Now, on some of these exponentials that we'll encounter, a lot of them, matter of fact, we are going to have or use what is known as the natural base E. We're going to do several applications of exponentials, and E is going to come up a lot. And E, turns out it's a number like pi. You know, pi, we say it's 3.14, that's an approximation of it. Well, you may not be as familiar here, but there's another number called E, and E is approximately 2.72. I've written several decimal places out, but it is like pi, it just keeps going decimal-wise. Matter of fact, the next four are 1828, so it looks like, well, it's going to start repeating, but guess what? The next number is 459. Yeah, it just keeps going, going like that. So it's about 2.72. However, it's like pi in that most calculators do have an E button on them, and so we're going to use that. So we don't have to remember even that it's 2.72. We'll just let the calculator do the work for us as far as the number goes. It's called the natural base, like I said, because it is naturally occurring in a lot of applications. So we are going to use that. So let's just evaluate a couple of, see if you can find your E button on your calculator, because we are going to use that quite a lot. E cubed, all right. So on mine, let's see, E is, you might see an LN button. They tend to run those together there, so you look for the LN button. It might be, mine's right above the LN button on my calculator. Yours may, it's E to the X button. Yours may be somewhere else, but find that. Let's see, E cubed, so E to the third power. Yeah, so it's 20.0855. Yeah, so to three decimal places. I mean, 4 decimal places, 20. For some reason I had that on my paper. 4 decimal places. 20.0855. Now, let's talk about E to the minus 5. E to the minus 5. See what you get there. E to the minus 5. And so, yeah, most, my calculator is this way. Most calculators, to do that negative power, you don't hit the minus button. You hit the subtraction button. Don't hit the subtraction button. You hit the negative button, which mine's right below my 3 on my calculator. So I wanted to mention that. So it gives me 4 places 0.067. Approximately 4 decimal places out there. All right. So yeah, so like I said, what I want to look at are some applications of exponentials. So let's use this first one. They don't all have E in them, but let's look at one here that does have E in it. All right, so the population of a country grows exponentially with growth rate 1.2%. All right. And so that'll be significant that we'll see this growth rate if it comes up in the actual equation that we have here. All right. So here it is. So the population after T years is population P of T equals 1.32 E to the 0.012 T And the P here, the population is in billions. T is in years, but P is in billions. It comes out in billions here. All right. Okay, so first of all, like I said, notice here that my rate, my growth rate, does show up in this population model here, the equation, because notice this, 1.2% is my growth rate, but look here, 0.012. What is 1.2% in decimal? If I get rid of the percent sign, I don't think we've done any yet where we had to deal with percentages, but yeah, to change a percentage, get rid of the percent sign, you move the decimal point 2 places, don't you? 2 places to the left, 1, 2, and so that is 0.012. Hey, how about that? That's my growth rate. Yeah, it turns out that in that exponent, you do have the growth rate. So there it is. Now, this is an exponential model because notice my variable, I switched over to t now instead of x. I have t, but t is in the exponent. And so, yeah, so this is an exponential model, an exponential equation to model this population growth. And then, of course, yeah, E, we got the E there, so that's the number we're talking about here, 2.718, blah, 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 okay? All right. So, question here, what is the population after 15 years? What is the population after 15 years? Okay, so that's my t value, so I'm going to evaluate p of 15. So that's 1.32 e to the 0.012, and of course that's times t, so times 15. So what I would definitely recommend here is go ahead and multiply your power out here. So it's 1.32 e, multiply that out, it's usually not too terribly much to do that. 0.18, yeah, turns out real nice there. For that particular one for sure. E to the 0.018. So now let me just punch that in. 1.32 times E, there's our E again, to the 0.18 power 1.58 is what the equation gives me to 2 decimal places. That's my population from the equation. Now, of course, doesn't make sense that the country would only have 1.58 people, and so yeah, so that is 1.58 billion people. It's a fairly large country, not quite United States size, but yeah. All right. Now, one other note here. I don't know that they'll ask you this, but see this 1.32 here? If we plug in year 0, we'll get e to the 0 at the end. Yeah, that 1.32 billion, with the billion on there, that is the starting population. So this is a positive growth rate. So we've grown in 15 years from the 1.32 to the 1.58. I mention that because let's compare that one to, with that growth rate there, to this population model. P of t, new population, is 6.4 e to the minus 0.023 t. E to the minus 0.023 t. All right, so in some of these questions, it's going to ask you, it may not ask you what the population after blah, blah year is. It may ask you something about the growth rate. What's the growth rate for this one from our previous discussion? Over here, it was P of t equals 1.32 e to the 0.012 t. That was our model on this one. And my growth rate was R, let's call it, was 1.2%. What's R over here? This is R right here, right? R is negative 0.023, which in percent, what is that in percent? Well, this we're changing the other way. We're putting the percent sign in, and so move the decimal point to the right. That's negative 2.3% is my growth rate there. What do you think the negative means? Well, this has a positive growth. The population's growing. So if you have a negative growth rate, yeah, obviously, hopefully, obviously there, you know what that means. It would mean the population is decreasing in that particular model. So population is going downward instead of upward when you have that negative growth rate. And so I just wanted to point there out again. Some of the questions that you'll have to be answering there are just about the growth rate, comparing the growth rates, which ones have negative growth rates, because it might, it's not going to tell you. You'll have to recognize it from the formula. So I did want to mention that. Okay? All right. Now, let's talk about this one. The number of bacteria after X days is y equals 300 parentheses 4 to the x. How many bacteria are there after 5 days? So, yeah, so here we changed a couple of things, obviously. One thing is that now we have base is 4. We don't have the e there to the x power. We have 4 to the x power. It's a little bit simpler, matter of fact. So that's one thing. And the other thing is the time here is in days. Yeah, I don't know. I don't think any of them have where it mixes up the units. I could have said 5 weeks. Well, the thing's in days. So just pay attention to that. It could very well do that. But anyway, the previous model were in years. This is in days. So just pay attention to that sort of thing. This, though, the x is in days. So that is our x. All I have to do here, saying a lot to just say, you just plug in the x and be 5. Okay? But it's not e in this case. They don't always have to have it for these growth models like that, an e to a power. So it's just 300 times 4 raised to the 5th power. 307,200. All right. Okay. All right, now, one of the big applications that we're going to talk about here in this particular section is going to be compound interest. So let me dive a couple of times into here to a couple of problems involving compound interest. Turns out, if you have compound interest, having an account that's drawing interest, or you're paying interest, also applications there, but it turns out it's an exponential function. It is exponential. So let me write out the formula and the words here that goes with it. So if principal P is invested in an account with interest rate R, that is compounded n times per year. It is compounded, it's called compounded n times per year. And we'll talk about the different variety of those we can have in a second. Then, the amount A, we usually designate the amount that it grows to, future value, sometimes it's called, after T years, is this. Here's the formula. A equals P times, parentheses, 1 plus R over N, and here's where the exponential comes in, 2 raised to that, parentheses stuff, raised to the NT power. Compound interest formula. If you haven't seen that before, that's what that is. Compound interest formula. A equals P times 1 plus R over N to the NT power. So, yeah, there's a lot. Spelled principle wrong there, but there's a lot going on in there. Yeah, P, principal, that just means the amount you start with. So we're starting with P goes here, kind of like the initial population. We talked about that a little bit the last example or two, but it's just the amount you start with. It goes here. The rate R, you divide that by the number of compoundings there is per year. We'll talk about that. And then raise all that parentheses stuff, raise that to the NT power, N times T power. Okay? So let's do a couple of those. See how those work if you haven't done them before. All right. If $5,000 is invested at a rate of 3.56%, find, number one, the amount after 5 years if it is compounded quarterly. Quarterly is our compound. Okay, the amount after 5 years. So let me copy that formula right here again. A equals, that's going to be what this equals, P times 1 plus R over N to the NT power. So yeah, so on these, it's just a matter of plugging in the numbers in the right places, figuring those out. Okay, so like we said, P is just the amount you start with, so this is starting with $5,000. 1 plus, R is just the rate, so here's R, 3.56%. However, that does need to be changed over without the percent sign. Move the decimal point and get rid of the percent, you move it to the left, so 0.0356 is what that would be once we move the decimal. So that's my R. Which brings us to the N. So N is the number of compound per year. N times per year. So I'm compounding quarterly. Quarterly means 4 times per year. There you go. N is 4 when you're compounding quarterly. We'll take a look at some others in just a second. But yeah, if we're compounding quarterly, 4 quarters in a year. It's the name. Okay. So N is 4. Then we're going to raise that to the N times T power. Well, N appears in this thing twice, so double duty there. And then time and years. Again, I don't think they'll switch units on us, but be careful that it does give you the years here for the time. Okay. All right, so here's, that's what we need to evaluate. Now, let me show you here how to enter this in, because the problem you run into, especially when it has to be pretty accurate, is the rounding. You really don't want to round until you get to the end. So here's my guidance on that. Let me just do one thing here. I'm not going to actually evaluate this in parentheses. All I'm going to do here is say 4 times 5, that gives me 20. And that's how I'm going to enter this in. Do what you want, I guess, but I'm telling you, if you round it too much, you're going to lose accuracy, and it's probably not going to like it, okay? That's exactly how I'm going to enter it in on my calculator here in just a second, just as that appears. 5,000 parentheses 1 plus 0.0356 divide by 4, and then raise that to the 20th power. Use that power button there, okay? That is my thoughts on that. Okay. So 5,000 parentheses 1 plus 0.0356 divide by 4. Raise that, power that up to the 20th power. 5,969.42. Of course, this is dollars and cents, so round this to the nearest cent. 5,969.42. 5,969.42 cents. Dollars and 42 cents. Okay. All right. Question? Let me know. Okay. Now, number 2. Let's do the same 5,000, same rate, but let's do this. Number 2. Find the amount after 25 years if compounded semi-annually. That seems like another one that the problems that I picked out they're fond of. Semi-annually. Quarterly, this one's semi-annual. 25 years, so that changed our T. Now it's 25 years. Semi-annually, okay. Annually, they also sometimes give you annually. Annually, of course, is just one time per year, but semi-annually, that divides it into 2. So if it's compounded semi-annually, that would be 2 times per year. So that's going to mean in our formula, and it's going to be 2. So here we go. A equals, so we have the same P, we're starting the same 5,000. 1 plus R over N, so the rate stayed the same, 0.0356, I didn't change that one here. Divided by N, so N here is 2, so divide by 2. And raise that to the N times T. So that's 2 times 25. And basically, like I said, get that right, that's pretty much how I do it. Just, multiply this out to 50. So I'll put it in just like that and raise it to the 50th power. Okay? See what you get. See if yours matches mine. 5,000 parentheses 1 plus 0.0356 divided by 2. Raise that to the 50th power. Yeah, so we've grown quite a bit. 12,000. 80.70 is 0.076. So yeah, round that up to the next one there. 0.71. A little over 12,000. Okay. Now, one other, let's call it 2A here, problem. How much interest did they earn, or whoever it is earn? How much interest was earned here over these 25 years? How much interest was earned on number 2 there? Well, yeah, we're not, so this is, the one thing about this particular model here, we're not contributing any other amount to it. What we put in, 5,000, that's what we're just growing this with interest. And so whatever is over the 5,000 here, that's in interest. And so if it asks for the interest earned, it just wants you to take the final number and subtract it from your principal, what you started with there. 12,080.71. Subtract off the 5,000 that you started with. That's your interest. Was that 7,080.71 cents? Yeah. So there's no real big calculation there. You're just taking whatever you got and subtracting what you started with. Yeah. Since that's the way this works. All right? Okay. Well, let's talk here about another. Oh, before I do that. Okay, so we did quarterly, n equals 4, semi-annually, like I said. Also, other compoundings here. So we have annually, like I said, that's just n equals 1. Quarterly, semi-annually, n equals 2, quarterly, n equals 4. Monthly, I don't remember seeing that one, but obviously 12 months in the year, that would be n equals 12 compoundings, 12 compoundings per year. One other one I'm thinking of real quick here, daily. And I've seen it different ways, but I believe in this particular chapter here, the daily, well, we're going to go with the non-leap year, days in the year, n equals 365. I think I've got a problem coming up here in a second using that, but I believe those are, as far as that formula goes, the ends that you might encounter. Now, let's talk about, however, another compounding that we could encounter here. And actually, it's kind of nicer. And that is compounding continuously. I didn't. I did not point out, or we haven't done one where we could look at this, but yeah, the more compoundings per year, the better. So semi-annually is better than annually. Quarterly, it would be better to get that compounding than semi-annually. Then monthly would be better than that. And then of course daily would be better than all of them, because it's just the more compounding, the better. We didn't look at a particular problem. We could test that out, but that is the way it works. Now, compounding continuously, well, that's even better than daily. Continuously, so there's no break in the compounding. It's just compounding continuously, as the name says there. Well, if you get compounded continuously, the formula shrinks down quite a bit. Instead of having that kind of long one, it's just this. If it's compounding continuously, then it's A equals P times E raised to the RT power. Which, as you can see there, so that encompasses or takes out any mention of n, because it's compounding continuously, there's not an n value that you can put on that. But it also puts in this application, like we said, an application, this E pops up. The base there is just E. And so it does shrink the formula down quite a bit, so it makes it nicer in that regard. Easier to remember. It looks like PERT, almost looks like the word PERT there, but anyway, that's what it is. If it's compounding continuously, any of these others, of course you're using the longer formula there, but if it's compounding continuously, then we are going to use the PERT, okay? So, how much is in an account after 8 years, if $60,000 is invested at a rate of 2.9%, compounded continuously. Yeah, so those are the words that we need to see to use the PERT formula, compounding continuously. So to figure this one out, we're going to use A equals P e to the RT, which, you know, the E is the E, but the P, the R, the T are the same thing that it was in the other model, the other equation there. P is the amount you start with, so that's 60,000 here. E, the R, of course, is the rate, but it's 2.9%, so you do have to move that 2 places back to the left, so it's 0.029. And that is a change from the other one. The rate is actually in the power, times the T, time in years, so this is 8 years. That's what we need to figure out. Now again, that power, I'll go ahead and multiply that out. It's a little different. A while ago we just had to do 2 times 50, 4 times, I don't remember what the other number was, but anyway, that's pretty much what all I would do here before I enter this in is, all fully there, just go ahead and do 0.029 times 8. You get the power, it's 0.0232. And then just enter that in as is looking there. Okay? 60,000, then you find your E, then do that to the 0.232 power, 75,660. $75,667.18. Nearest cent. Okay? All right. All right, so let me do one more of those here. One of the other things they do is have you compare to, so it's pretty much the same, just you got to compare to at one time here. $50,000 is invested, or is to be invested. We have two options. A little something different on each one. Plan 1 has 4%. 4% compounded daily. And then plan 2 has 3.9%, but it's compounded continuously. So we said if everything else is equal, compounded continuously is better, but in this case we've got percentages are a little bit different, so let's see about that. Which has more after 20 years? So which one's better? Which has more after 20 years? Okay? So we're just doing a little calculating using our formulas here. So plan 1 is compounded daily, and it's 4%. Which do you think is going to have more? Compounding continuously is the better compounding, but you got a better rate. Let's see. All right, so plan 1 after 20 years, we have this. Well, it's compounded daily. And so that one, we have to go back to the first formula, A equals P times 1 plus R over N to the NT power. Right there. To go with that. All right. So our principal amount we start with, 50,000. That's P. 1 plus, the R is 4%, so that's, so if it doesn't have the decimal's right behind the number, so move that decimal point 2 places back to the left, so that's 0.04 is my rate. N is the number of compoundings per year. Well, if it's daily, 365, that's what we're going to use. N is 365, so it goes under the R, and then it goes up here with the T, 365 times your T, time in years, 20 years. All right, once again, to calculate that, I would not try rounding that off. That's going to be a mess of a decimal. 0.04, you're dividing that by 0.365, so it's going to be 0.00 something something. And you don't want to even round that off because